What if I told you almost everything in the universe is invisible? Look up at the sky. Look around you. Every star, every galaxy, even you, all of it combined adds up to just 5% of what exists. That's it. Just 5%. So what's the other 95%? We know it's there. We can see its effects, but we don't know what it is. Here's what we think we know. About 68% of the universe is something called dark energy, a mysterious force that causes the universe expansion to speed up. The remaining 27% is dark matter, a substance that has more total mass than everything we can see combined. Even though dark matter makes up only about a quarter of the universe, if you ignore dark energy, roughly 85% of all matter is dark matter. Dark matter cannot be seen. It neither emits nor absorbs light. We know it exists only through its gravitational effects. This is without a doubt the single greatest mystery of all time. So how do you find something you can't see? We are launching the biggest hunt in history, from the quiet of deep space to the most powerful machine ever built by humans. And the winner could literally rewrite reality itself. Discovering dark matter would upend particle physics and cosmology, potentially forcing us to rewrite fundamental laws. Before we start the hunt, you need to see the evidence. How are we so sure that most of the universe is invisible? The clues are absolutely everywhere. The first clue is completely insane. Imagine a solar system. Planets farther from the sun orbit more slowly because gravity gets weaker with distance. That's basic physics. But when astronomers measured how stars move in other galaxies, they found something shocking. Stars at the very edge of galaxies were orbiting just as fast as stars near the center. Based on the matter we can see, those outer stars shouldn't be able to move that fast. They should fly off into space. The best explanation is that galaxies are surrounded by a vast, invisible halo of matter providing extra gravity. This invisible halo is thought to be dark matter. The second clue is even crazier. Einstein taught us that massive things bend space. So when light from a faraway galaxy passes by something heavy, it gets bent. This is called gravitational lensing. Gravitational lensing lets scientists map and weigh dark matter, because its gravity bends light even though it emits none. Scientists pointed their best telescopes at the sky, and they saw it happening everywhere. They saw light from distant galaxies being stretched into these beautiful arcs. By measuring how bent the light is, they can literally weigh the thing that's bending it. And every single time there is way more stuff than we can see. It's like seeing the shadow of a giant that isn't there. The evidence is overwhelming. Something massive is out there. It's the biggest mystery in the universe, the case of the missing matter. And today, we're meeting the people trying to solve it. Scientists are pursuing two main strategies to uncover dark matter, each offering a different set of clues. First, you have astrophysical searches. These are teams of astronomers using the most powerful gamma-ray telescope ever to scan the entire universe, the Fermi Large Area Telescope. Their strategy is to find dark matter by seeing what it does to everything else in outer space. Dark matter is invisible, but it bends, heats, and distorts the visible universe. So astrophysicists look for these effects, not the dark matter itself. They are patiently watching the cosmos, looking for the fingerprints this invisible ghost leaves behind, gamma rays. Then you have the team at the Large Hadron Collider. Deep underground in Europe, it's a 16.6-mile-long ring where physicists are taking a much crazier approach. Their philosophy is simple: create the right conditions for dark matter candidates to appear. Here they smash particles together at almost the speed of light. They are trying to force this invisible enemy out of hiding by creating it right here on Earth. These two teams, the watchful eyes of Team Space and the power of Team LHC, are humanity's ultimate attack on the biggest mystery in science. Astronomers are looking for dark matter clues in the most extreme places in the universe. Some theories predict that when two dark matter particles meet, they annihilate and emit gamma rays, making the crowded center region of the Milky Way an ideal place to look. Since 2009, NASA's Fermi Large Area Telescope has monitored this region and detected an unexpected excess of gamma rays, but its cause remains uncertain. It could be dark matter annihilation, or could come from many faint spinning neutron stars called millisecond pulsars that are too dim to see individually. Millisecond pulsars have been detected in radio, X-ray, and gamma ray portions of the electromagnetic spectrum. Millisecond pulsars are not dark matter sources, they are dark matter detectors. Their clock-like precision allows astronomers to sense the gravitational fingerprints of dark matter throughout the galaxy. And then there's the Euclid satellite. Euclid is a European Space Agency space telescope designed to map the dark universe, specifically dark matter and dark energy, by observing billions of galaxies across more than 1/3 of the sky. By measuring the light from billions of galaxies, Euclid will create the most detailed 3D map of the universe. The most precise and complete dark matter data from Euclid will be available by 2031. If astronomers are trying to listen for a whisper, the teams at the Large Hadron Collider are creating tiny controlled collisions to see what appears. Inside the Collider ring near Geneva, Switzerland, protons are accelerated to speeds extremely close to the speed of light and smashed together. Each collision produces a brief microscopic fireball with enormous energy, allowing new particles to pop into existence from that energy. Experiments such as ATLAS and CMS wrap the collision points in layer after layer of precision sensors, recording every trace a particle leaves behind. It's tracked through the detector and the tiny bursts of energy it deposits, so physicists can rebuild the moment of creation. One aim of these experiments is to search for new particles and phenomena, including possible dark matter candidates. So how do you detect a particle you can't see? You look for the footprints it should have left behind. At the LHC, particles collide at enormous energies. In each collision, the visible debris must balance. The detectors, like ATLAS and CMS, track almost everything that flies out: charged particles, photons, and sprays of particles called jets. When the protons collide, they're only moving forward. So after the collision, the sideways motion of the debris should cancel out. If it doesn't, that imbalance means something invisible carried some of that sideways motion away. That something shows up as missing transverse energy, one of the key signatures physicists use to search for dark matter. These searches have been run on billions of collisions. So far, every imbalance can be explained by known invisible particles such as neutrinos. If dark matter were produced, it would look the same. No light, no tracks, just a silent escape carrying momentum away. But each time dark matter doesn't show up, scientists can rule out another theory about what dark matter could be, which helps them search in even better places next time. No confirmed particle in the standard model of physics can explain dark matter. For example, particles like electrons, quarks, and photons. None of them has the right combination of properties to be dark matter. For decades, physicists bet on one leading idea: the WIMP, the weakly interacting massive particle. The WIMP theory was so compelling, it dominated dark matter research for decades. If WIMPs existed, the early universe would naturally produce exactly the amount of dark matter we observe today, with no fine-tuning required. That coincidence was so striking it earned a name: the WIMP miracle. The Large Hadron Collider was perfectly positioned to test this idea. Smash particles together at high energies, and WIMPs should appear, slipping invisibly through the detectors, leaving missing energy behind. After years of searching, nothing beyond known particles has shown up. No WIMPs, no miracle. That failure changed everything. Physicists were forced to widen the search. Now the spotlight is on a whole zoo of new possibilities. One leading candidate is the axion, a particle so incredibly light it behaves more like a vibrating field than a particle. Physicists originally invented axions to fix a puzzle in the strong nuclear force, but they turned out to have exactly the right properties to be dark matter. If axions exist, they might also be the invisible stuff called dark matter. that holds galaxies together. Scientists haven't found any yet, but new experiments are steadily ruling out possibilities. This hunt is nowhere near finished. In fact, it's about to get even more intense. At CERN, they're getting ready for the high luminosity LHC, a massive upgrade that will increase the number of particle collisions per second by up to 10 times the original LHC design value. More collisions mean far more data, enough to reveal extremely rare phenomena that the current LHC might never see. In space, the revolution is just beginning. The Euclid mission will map the dark universe for 6 years, which officially began on February 14, 2024. Next comes the Nancy Grace Roman Space Telescope, scheduled to launch no later than May 2027. It's built to tackle 3 major questions. Regarding dark energy, how has the universe's expansion changed over time and what's driving it? Regarding exoplanets, how common are other worlds in the Milky Way, especially the ones too faint or distant for the Hubble Space Telescope or the James Webb Space Telescope to detect? And finally, regarding dark matter, how is the invisible dark matter structure distributed across the universe, and how does it shape galaxies? Its entire mission is built around surveying the sky far faster and wider than any previous NASA telescope. The shift is moving from let's look everywhere and see what we find, to we know exactly what to measure, and we're measuring it with extreme accuracy. The hunt is getting smarter and much, much faster. If you're fascinated by this exploration into one of the biggest mysteries in the universe, make sure you subscribe for more content like this. And let us know in the comments, what do you think of the search for dark matter? Or what quantum or cosmic topic do you think we should explore next? So 85% of all the stuff in our universe is still a complete mystery. We are floating in an invisible ocean that holds our entire galaxy together, and we have no idea what it is. So far, the hunt has come up empty, but empty is probably the wrong word. Every dead end has just shown us how insane this mystery really is. We've learned that dark matter is way sneakier than we ever thought, and finding it is pushing our technology to the absolute limit. The universe is hiding its biggest secret right in front of us. And that's exactly why with every single collision created and every image from space, we get one step closer to turning on the lights in the hunt for dark matter. Until next time, remember, stay curious and keep exploring. Thanks for watching.